Thank you everyone for coming. This might be the biggest audience, definitely on the bigger side. This is the fifth in a series of lectures that I've been sort of touring and giving. The slides are improving each time. Hopefully this will be the best one yet. Good, Jam. So before I start discussing the Jam protocol and what it is, what it's trying to do, where it fits in, I want to talk a bit about the wider context. I'm thankful for Obi for giving a bit of historical context for where this is all coming from. But I want to go a bit deeper into specifically Web3 and this sort of industry. I want to start by sort of pointing out that the industry is kind of forking. It's been forking for quite a long time, but it's becoming more and more clear that different operators, different projects, different people in the industry are really sort of going in one of two different directions with their sort of innovations and their outlook and their attitude. On the one hand, we see some projects, of which I count Polkadot a leader, thinking much more in terms of the long-term goals, long-term thinking, long-term benefits for this technology. And we see efforts for actual decentralization, while still obviously trying to be stable, scalable, and so forth. Efforts for things like light clients, so we don't have these random points of trust within a otherwise possibly decentralized ecosystem. Again, bridges, oftentimes a point of attack, oftentimes a weak point between potentially otherwise reliable and resilient systems, and so on. There's a lot of different points here that we have to get right in order to make these systems like actually viable long term, like useful. On the other hand, we see a lot of groups who are trying to take maybe some of the elements of that Web3 has introduced, like easy tokenization, but actually throw away all of the things that have up until now made it actually resilient, reliable, the other principles of Web3. Essentially trying to isolate some of the use cases and throw away or cut corners where, in order to achieve some sort of whatever scalability or accessibility for wider population, they've disregarded key elements of Web3. Polkadot is very much situated in the long-term side, which means certain short-term, certain gains that one might get from the short-term side are not quite so evident. But it's only with long-term thinking that we're going to make systems that continue to be useful years from now. These four things are not the same. They are linked, but they're not the same. DeFi is really just a particular use case of technology. The fact that, the D starts for is for decentralized. Oftentimes, DeFi systems are not actually very decentralized. A lot of corners are cut with these systems in an effort really to emphasize the FI part, right, the finance. Blockchain is a technology that helps us deliver some of these use cases. Cryptocurrency is another use case, although it could also be considered a sort of resource for creating scarcity, for creating certain economically useful signals. Web3 as a whole is essentially an approach. Right? It's an alteration of how we approach technology and how we approach systems that we're trying to build, where that we want to sort of serve multiple people, oftentimes globally distributed, who don't necessarily know or trust each other. So Web3, another way of thinking about it is it's sort of a sort of technological basis for this less trust, more truth principle. The point of this less trust, more truth, because having less trust seems kind of not so good. But actually what we're talking about isn't so much trust itself, but the requirement to trust. We want to have less of a requirement to trust, right? Trust is sort of a bit of a neutral thing. It's like faith. It's like you can have it or you don't. It's your own personal, it should be your own personal choice. But systems that require us to trust, that's like requiring us to have faith. That's not a good thing. Yeah. Unfortunately, these systems, oftentimes there is no real alternative for societies of our size. Once upon a time where villages were basically 50 or 100 people big and you didn't really need to interact outside of your village too much, you could avert the need for trust. You would actually have full knowledge of everyone in and everyone's history that you might possibly be interacting with. That's not the case anymore. Right? And so to some degree we need trust, and we can't trust literally everybody, that wouldn't make any sense. So we tend to create these icons, right? These institutions, and we trust the institutions or the organizations or the companies or the governments or whatever else. This has key problems, and we've seen some of these key problems play out over the last 15, 20 years in very recent history. Indeed, the creation of Bitcoin. Bitcoin, at its creation, referenced one of these key breakdowns of the trust-based system, right? The 2008 banking crisis. Well, how do we avert the need for trust yet still retain this size of civilization, right? Of society? Well, it turns out that with information systems of the complexity and sophistication that we have today, we can actually introduce a new concept that we wouldn't ordinarily, rewind back to the 90s, have been able to utilize, and that is truth. It's essentially the ability to try to spread truth in order not to need so much trust. So Web3 is, obviously it's been hijacked somewhat as a buzzword, and it's oftentimes used interchangeably for like NFTs and DeFi. But Web3, according to the Web3 definition that I posted way back 11 years ago, is really about building resilient systems, a secure social operating system was how I actually phrased it back then. These systems will tend to be decentralized, because this is the way that we avert the need for trust. They'll tend to be verifiable, because this is the way that we avert the need for trust. Self-sovereign, interoperable, privacy-preserving. These are things that these 5 things are sort of terms that Sean, who authored these slides, brought to the discussion. My maxims over on the right side: resilient, general, performant, coherent, accessible, are all really more. They are Web3, but they are quite specific to blockchain technology in particular. And we have things like the pillars of blockchain that Andreas Antonopoulos, a Bitcoin luminary, proposed. And again, these things are all sort of dancing around the same basic idea, which is trying to make resilient systems, trying to make systems that stand up to the entire world, right? All possible malicious forces, to the point that these systems can exist autonomously. So Web3 is actually a fundamental change in how we approach globally interactive systems, right? How we design web services, massively multi-user applications. And it requires a certain perspective change in order to actually create effectively Web3 systems. Okay. That's Web3. Blockchain, what's blockchain? Blockchain is basically just a decentralized computer. I say just a decentralized computer. These things are actually pretty hard to engineer properly. But it's a computer. It's just a computer that doesn't have a physical form. Most computers, like this very laptop, have a physical form, right? It's right here. It's not over there, and it's certainly not in New Zealand or London, right? It's here. If I want to, I can put it on the internet, right? And so I can open up an SSH port and SSH into it from somewhere else. But that doesn't make it decentralized. Yeah. Ultimately, whoever's next to it can turn it off. They can pull the power, rip the battery out, smash it with a hammer. Yeah. It has a fundamental weakness as something which is serving across the internet, serving people, in that it has a physical form. Yet the internet is not a physical thing. So a decentralized computer is actually a computer that exists on the internet, like fundamentally doesn't have physical form, fundamentally doesn't have all of these problems that we get with computers of physical form. Decentralization is not the same as distribution. Distribution is a process or a technique that we use to essentially scale something, or potentially to some extent reduce geographical latencies. It's decentralization. I actually, in a long ago conversation, we're chatting about, Vitalik and I were chatting about decentralization and distribution, and how we can possibly, how these terms could be distinguished for people who aren't used to this Web3-esque, blockchain-esque, peer-to-peer-esque thinking. And one of the terms we came up with was political decentralization, right? It's not that there are lots of machines kind of contributing to a problem. It's the fact that they are operated by economically independent entities, economically independent actors. And it's only through this type of decentralization that we get the benefits. Yeah? What Google does, or what Facebook does with its servers, they decentralize to some extent, right? In that there isn't a single data center that hosts them all. But it's not the same thing as what we mean here. Really what they're doing is distributing their computational resources in order to gain some of the benefits that we would get from decentralization. Yeah? They actually get other benefits as well. Parallelization. You don't necessarily get parallelization from decentralization. Yeah? And we see a lot of decentralized systems that are very much not parallelized. I'll go on to that in a second. Now, history sort of, if we can kind of track computers through history, we can track a lot of things through history, but let's take computers as an example. There were early computers. These were very, very domain-specific things, right? The first computers were really just there for one particular mathematical problem, right? To calculate a certain equation, a certain formula. Over time, computers evolved and they became less domain-specific. They became somewhat generalized, yeah? In the 80s, 70s, 80s, 90s, we saw business servers, mainframes, develop. Go on a bit further and we see that generalization move into commoditization, right? And we see this is sort of the end of the line, essentially, where it's almost fungible. It's kind of a fungible service, right? We don't care too much about the specifics of the machine, right? We only care about some performance metric, but that's about it. We see the same thing with blockchains to some extent. Early blockchains, very domain-specific things. Bitcoin, super domain-specific, yeah? Then we get sort of business-specific blockchains where they're more general, but they still are made on a sort of, there are still key differences between them. That's sort of actually where we are today. We're not really at the cloud revolution yet, but we are approaching the cloud revolution. And some of the stuff that I'm talking about today is really what that's about. So trying to rephrase the difference between Web 2 and Web 3. Web 3 is about resilience, yeah? And it's about building decentralized computers and things that they sort of interact with, also tending to be decentralized, that are resilient against various malicious forces or various malevolent forces. Indeed, there is generally no concept of a benevolent force in Web3, in proper Web3 systems. There is only the world, and the world cannot be trusted. Yeah? There is no, normally, if we have like a sort of centralized system, a traditional system, there will be at least one benevolent force in the world. An example, this laptop, the benevolent force is me, right? I want to look after my laptop. I don't want it to break. So I'm not going to hit it with a hammer or like hack into my laptop. It serves me and therefore I look after it. I am a benevolent force from the point of view of this laptop. Yeah? Take Google servers. The Google organization, and to some extent its employees, are a benevolent force for those servers, from the perspective of those servers. The company is a benevolent force. The company has total control and ownership over them, and therefore, why would the company want to break its own servers? Why would it want to harm its own servers? No, it wouldn't. So the company is a benevolent force. Web3 systems don't have the same thing. They don't have benevolent forces that they can rely on and trust. Yeah? And this is a key perspective shift. Web3 systems have to be resilient because they have to exist in the world autonomously, on their own, without a benevolent protector who is going to make everything okay. And understanding this allows you to understand how we approach engineering Web3 systems. So we've seen a few step changes in the world of blockchain. Bitcoin was essentially, a bit like a calculator. It was basically a financial payment system, kind of bank-esque, domain-specific computer. Ethereum made it more generalized, and it sort of took Bitcoin from this highly domain-specific position that it was in, the technology, I should say, and manifested technology that was much less domain-specific. It was sometimes called Turing complete. It's not actually Turing complete, and this is an important point. Its scripting language, or the EVM, is Turing complete as a sort of language, in that you can write programs in it that would be Turing complete. But its execution environment, so the place where those programs run, is not Turing complete. It's not Turing complete because it has a fundamental gas limit. The gas is the number of computational steps that the program's allowed to take before it must finish. And this is finite, and it's actually quite small, but more importantly, it's finite. This makes it not Turing complete as a computer. Yeah, it's just that the language that the computer uses is Turing complete. That's a key difference to Bitcoin, where the language that the Bitcoin computer uses isn't even Turing complete. Now, Polkadot takes this concept and essentially is trying to create a cloud instead of a computer, right? A much, much bigger, more pervasive, more general computational resource. How do you build a cloud? Well, you start with a computer. I mean, ideally, you start with a very powerful computer that can, expose lots of, or maybe not lots of, but specifically useful, general, flexible resources, like storage, for example. Ensure that it's essentially commoditizable, so it needs to be extremely low cost. And then you make sure that the computer can be composed, so it can be essentially connected, but in a rich way to other computers, so that you can essentially create software and services that exist over many of these things. What's the resource of Web3? Well, I'm not sure if there is just one resource. You could argue that storage, like decentralized availability, would also constitute a resource. But certainly the main resource of Web3 is block space. Essentially, what is block space? Well, it's computation, right? And to some extent, storage. Well, my computer does computation. Does that mean it has block space? No. Crucially, block space is decentralized or resilient computation. It's computation that cannot be altered by any particular economic force, right? And the more that the more secure it is, the less that it can realistically be altered, the more Web3 it is. We can kind of measure this, the quality of this block space in a few different ways, and I'll talk about that in a second. But the crucial thing is, it's really just computation. It's really just the thing that a computer provides with you. It's just that it's resilient. It's resilient against the economic forces of the world that we assume, because it's a Web3 system, are ultimately going to be, from the perspective of the Web3 system, malevolent. Now, Polkadot is designed to create the highest quality block space, right? That's why we're here, right? We're not cutting corners. We're going for the throat. So, one of the ways that we can measure it is by computational throughput and data throughput. Now, transactions per second is is a very imperfect way of measuring computational and data throughput of a system, because transactions, it turns out, require both data and computation to be processed. Unfortunately, different systems process transactions in different ways. Indeed, different systems have completely different definitions, almost, for what constitutes a transaction. These transactions are the sort of proper transactions. They're like, and what, by proper I mean they operate on state that is independent of the other transactions that are happening at roughly the same time. They always include a signature, one per transaction. They always include a transfer, one per transaction. Sometimes we find TPS metrics that do not uphold these three things, and then that's where some systems have bloated numbers. In fact, some systems don't even require a transfer to happen at all. But anyway, as you can see, the number is substantially greater than any other system that is actually deployed. Of course, some systems claim theoretical throughput numbers. Other systems say that they had some particular deployed testnet behind closed doors. Yeah, whatever. This is for actually deployed live decentralized systems. Polkadot has the highest bandwidth, right? So if we just take data bandwidth alone, ignore processing, computation, it's still far higher than other data availability systems, other systems that are domain specific for data availability. In terms of the decentralization or the number of economic actors that would have to collude or be hacked or be malicious before the system breaks, Polkadot has by far the highest, right? This is by far the most decentralized system of anything that's handling any significant amount of funds. Ethereum, despite its efforts to decentralize through having lots and lots and lots of validator keys, actually, I think is this Nakamoto coefficient, or the number of independent economic actors that would have to collude to break the system, is only about 2 or 3. Yeah. And it turns out that Polkadot is the most energy efficient of the major chains, right? And there's a reason that it's energy efficient. Essentially, it comes down to scaling out, not scaling up. And that's what I want to talk about for most of this time. The way that it achieves this vast amounts of processing throughput, vast amounts of data availability in time, in part, is parallelization, essentially distributing the workload over its node network rather than trying to just get all of the nodes to replicate each other. It also it doesn't do this at a cost of tearing apart the network into separate, separately secured, sort of independent sovereign networks. That would be a problematic approach. That would essentially divide and conquer not the problem, but the solution, which is its economic integrity. Polkadot also, in order to create rich interoperability between its sort of separate portions of its system, really needed and pioneered interoperability. One of the things that we created and released was XCM, the cross-consensus messaging format, that really attempted to create a common format for actions allowing interoperation between blockchains. And of course, it has substantial very large and effective data availability system. All right, that's Polkadot. I want to talk now about Jam. So Jam is the next, the Polkadot governance essentially gave Jam the carte blanche, permission to be the next Polkadot protocol. This was voted on by quite a lot of people, and essentially now has been specified as, in a decentralized fashion, as the upgrade path for Polkadot. It's got a formal specification, the grey paper. For Polkadot, it means increasing its performance quite substantially and preparing it to become more in line with this concept of being a Web3 cloud platform. There's a lot of people implementing Jam. So the grey paper is kind of, I actually released the grey paper 10 years almost to the day, I think it's out by 1 or 2 days, from the day that I launched the yellow paper back in 2014. That was sort of on purpose. The grey paper and the yellow paper are are kind of similar in that they utilize similar formalisms and have a similar structure. The grey paper describes a more sophisticated system, obviously, as we learn more about engineering decentralized computers. They do tend to become a little bit more sophisticated. It's actually not that much bigger than the yellow paper at present. I think the yellow paper is about 55 pages. The grey paper is a little more. It's about 65 pages. So but they're definitely of comparable size. The grey paper is probably a little bit more complex in how all of the different pieces interact with each other. But still, it's not like a million miles away in terms of how difficult a read it's going to be. By having a grey paper, by having a technical, formal specification of the protocol, essentially by launching the protocol before we launch any piece of software that implements the protocol, we try to create an environment of diversity so that others can also implement this software. And I'm happy to say there's quite a few people around the world that have taken up this challenge and are busy implementing this protocol specification. Of course, I have my own implementation that's sort of sitting behind the scenes. I mean, I work on it, of course, with a team as well, a few other people. But this is not meant to be any sort of a reference implementation. This is just another implementation. The reference is the grey paper, and that's the thing that is public now, is very, hopefully, unambiguous. In addition to the paper attempting to create an environment for people to implement Jam, there's also a fairly substantial prize pool for anyone who wants to implement it and who thinks that they have the ability. It's 10 million DOT, which is still quite a lot of money. It's actually sort of split up into different sort of smaller prize pools that are earmarked for particular computer languages or sets of computer languages. 35 teams that we know about. I think there are probably one or two others that we don't know about, who are independent, totally independent, right? Really, like nothing to do with, as far as I know, certainly nothing to do with me, nothing to do with Parity, nothing to do with Web3 Foundation, are currently implementing this protocol. And they're using between them over 15 programming languages. Now, in addition to making, when we try and get lots and lots of teams, lots and lots of people who are not in the same organization, to implement a protocol that's only specified by essentially, mathematical formalisms, we run the risk of when we get to actual instantiation of the network, actually trying to bring this thing to life, it not really measuring up to expectations, simply because there will be the whole point of Jam and of generally decentralized peer-to-peer systems is that we're counting on the emergent effects of the system. It's not like where, if we're just having a sort of regular server-client architecture, where we're counting on the direct effects of the server. Yeah, we can literally engineer all the effects that we want directly in the server, and everything that we engineer will work exactly as we write it. That's what we want. So it's like, I have this problem, I need to have web pages served, then I will make a piece of software that serves web pages, right? And then it runs on a server and it serves web pages, and you can very clearly link the problem, or rather what it is that you want to happen, with the solution, which is how I actually make it happen, right? Those two things are basically one-to-one mapping. What I want to happen, how I make it happen. I just use a programming language. Unfortunately, with peer-to-peer systems, with actually decentralized, proper, crypto-economic systems, the two things are not linked anymore. What we're counting on is the emergent effect. The direct effect of a node is kind of useless. It's the emergent effect of 1,000 different nodes all interacting with each other that creates the system. Yeah. Creates the final thing that is what I want to happen, which is a distributed, decentralized computer. One node on its own doesn't give me that. And so this is about attempting to engineer this emergent effect to happen. Now, you know, we have some very clever minds working on this, and it's we have confidence that this is what the emergent effect will be, but it's hard to do it unless to debug. Yeah? Debugging emergent effects is really difficult because your debugger works at the level below the actual effect. So if it doesn't give you exactly what you want, you can't debug it directly. You can only debug the things that are sort of working together to individually. Yeah? Essentially, what you want is the forest, but you can only inspect an individual tree. Yeah? So having access to all of the trees in one place and ideally amalgamating all of that information again into a single place is really useful. We can't do this on a live system. Yeah, we can't do it because it's decentralized. We'd have to get literally all, well, first we have to know all the validators, and then we'd have to get them all to like send us all of their logs and log them into one place and hope that all the clocks were synchronized. It would be a mess, and it wouldn't be Web3. Yeah, it wouldn't be resilient. If any one person knows all the validators, that's kind of a potentially compromising piece of information for the system. So instead, we create a testing and experimentation facility that has all of the computational power that is required by the network to operate, but instead hosts it in a single place with a high power logging system. Yeah? Okay, essentially, we create a scale model of the network. And it's with this that we can actually do our experimentation, optimization, and see the whole forest all at once, not have to inspect a few trees here and there. And that's what the Jam Toaster is. It's not a supercomputer by today's supercomputer standards, but it's certainly no slouch. It's got 16,500 Threadripper cores, and these things go pretty quick, and an awful lot of RAM, 32 terabytes. So it's, you know, it's capable of doing the level of computation that we would need to actually simulate the whole of Jam. Good. So I've talked around Jam quite a lot. I'm sorry, I'm gonna talk around it a little bit more, but I hope I'm slowly zeroing on what it is and what it's trying to be. So what is Jam? I did a little picture of it there. It looks a bit like a flower. So let's go back to the driving factors. I mentioned this in a slide a few bits back with like what is Web3. These are how I like to think in terms of Web3, at least at the moment. So first and foremost, resilience. The first Web3 system, Bitcoin, the reason it was a Web3 system is because it's resilient. The others are all kind of nice to haves. The less you have them, the less useful the system is. But resilience is crucial. If it's not resilient, if it's fragile, then it's not Web3. It's just a regular system. It's Web2 or whatever. Our Bitcoin is obviously quite resilient because it's been around for so long, right? What is it, 17 years? So it's like, that's a pretty good indication that it's resilient. Bitcoin didn't have some of these other things. It's not very general. Yeah, you can't do that much on it. It's kind of good for what it is, but it doesn't do much else. And it's not very performant. Now, when we the key sort of move forward, the key sort of innovation that Ethereum provided over Bitcoin was introducing this concept of generality. It made it more general. Didn't make it perfectly general. As I said, it's not actually Turing complete, but it does have a scripting language that lets you write and execute a lot more interesting software than Bitcoin would provide for. Ethereum wasn't performant. Now, when we got to Polkadot sort of provided all three. And it was like, oh, right, job done, easy, because I didn't realize that there were two other things that we might want. It turns out that coherency, which is something that Polkadot sacrificed to get performance, is an important attribute. It's perhaps not as important. I think it's not as important as performance. Elements, the individual blockchains that exist within Polkadot are themselves coherent. But that aside, coherency is something that we would want in an ideal world. And obviously accessibility too. We want as many people to use it as possible. So, specifically, past work, Ethereum 1. Well, I've drawn it as this is my little drawing of it, take it for what it is. Not very scalable. Now, it turns out some people, just to explain the drawing, the dotted line on the outside is like the consensus, right? So it's like everyone has consensus. And then the thick line on the inside is the state, right? So there's like a single state. It's not very scalable. You can't, it's sort of like a cold-blooded creature. It's like there's a limit to how big it can grow, like a physical limit to how big it can grow. Yeah? This is actually an important consideration I'm going to go into in a second. People did try to scale this model. Right? I call this high-performance synchronous, or kind of just a scaled-up version of Ethereum. We saw different networks trying to do this in different ways. And they've over the last 10 years, right, we've seen various different attempts, essentially just trying to make Ethereum go faster, launched as a different network. Generally, these things are either centralizing or fragile, like they break a lot, or both. And ultimately, they're still going to hit this ceiling, right? Ultimately, the ceiling is just how fast can you make a single computer go? Like how many transactions can a single computer process? That's the sort of end game of this. Yeah, the end game of centralization is run it all on one machine. Yeah? And the end game of scalability, therefore, is, well, how fast can that machine keep up? If we don't have to worry about like replicating it across the world to potentially other machines that might not be as fast and might not have as fast of a link and da-da-da-da. But even if we do try to replicate it across and actually keep the centralization, we're not going to be able to scale, because then we're going to have not only it will only go at the slowest machine that's expected to keep up, but also we have the problem of replicating state, right? It's like as slow as that machine can keep up, but also as slow as that machine can like synchronize with all the other machines, send its data out, receive its data back from them, and so forth. These systems are not scalable. And we know this. Silicon Valley has a mantra. You scale out, not up, right? You can't expect this to work. It's just a bad direction to go in. So what are the other directions that people have gone in? Well, one of them is the one that sort of Cosmos introduced. It said, all right, we're not going to try and scale up. We'll try and have multiple different instances of chains. But then in order for them to interoperate, otherwise we just end up with tons of different systems that are not compatible. So actually we're going to build bridges. This was a big deal, right? So they have a bridge, and they have a consensus mechanism, Tendermint, which is very highly sort of easy to make bridges with. Problem with this is, of course, that each of the networks has its own security, has its own economic backing, its own capital backing it. Which means the network as a whole, if you expect causal interoperability between the networks, and this is the thing that you actually want, will end up being only as secure as the weakest participant. Yeah? You're essentially opening your doors to other potentially compromised systems. Now, something that came up is these are now different systems. These different chains are different systems. They each have their own state. They each have their own list of accounts. They each have their own smart contracts, right? They each do their own things. And to interoperate with something inside of the same chain as you is easy and fast and cheap, as it would be if it was all just a single system. But to operate with something in a different chain becomes expensive and slow and difficult, because it's in a totally different system. It's kind of like, you can very easily, if I want to set up a bar and I want to get some beer, right? Well, I really like British beer, yeah? So British beer is, it's sort of fermented, but it still has the bacteria in, which means, or the yeast, I guess, which means it takes time to happen, and then once it's ready, it lasts for maybe 5 weeks, yeah? And you have to keep it refrigerated at all times. This means if I'm opening a bar in the UK where the beer is brewed, then it's relatively easy, right? No problem. I just find a brewery and I say, right, I want some beer from you, and they deliver it every week or two. All good. If I'm in Japan opening a bar, it's a problem. Yeah. Now, at that point, I have to have, I can maybe put it on a boat, but then the boat might take longer than 5 weeks to arrive, and by the time the beer arrives, it's not so nice anymore. Maybe I put it on a plane, now it's super expensive. Maybe I try and put it on as like spare capacity in planes and then sort of pay a bit less, but then maybe it doesn't get there on time and then it's bad again. It's problematic, yeah? And this is the issue. If we have different systems, different states, and we partition our states up in this way, it's really hard for us to have full interoperability, yeah? It turns out that also engineering a new blockchain is kind of hard compared to just engineering a smart contract, raising the barriers to entry. Okay, what about Ethereum post, I don't know, 2029 or something, or Ethereum including its L2 rollups? Well, the different rollups so if you're not familiar, rollups are essentially ways of compressing correctness, right? So you can take a piece of computation that would normally take quite a long time to do, like for example, validating a block, and you can compress that computation into a much smaller piece of computation that demonstrates beyond reasonable doubt that the ramifications of that computation are correct. Yeah. And this is the basis for in some sense, or at least it was until a month or two back, scaling Ethereum. Problem is that the different approaches tend to have different trade-offs. Some approaches are what are called optimistic rollups. Some of them are called ZK rollups, and the different providers of these rollups kind of want some sort of USP. They want something that they do better than the other ones. So they'll often try to differentiate themselves, as you would if you were a business competing in a market. And what we end up with is this kind of patchwork quilt where it's kind of, you don't really get the same thing from the different rollups. Some might take ages before any effects on the rollup can actually take effect outside of the rollup. And if in some cases we end up with actually different security parameters. Many of the rollups are highly centralized. They have either a specific set of validators, they have very few validators, or they have a single agent who is generating proofs, allowing them for the possibility of stalling the chain on demand or censoring. But even more pointedly, we still suffer from this persistent state partition. The different rollups are different areas of state. Interacting within a rollup is generally cheap and fast and easy. Interacting between rollups is generally expensive, slow, and hard. Polkadot provides essentially a homogeneous rollup environment. So the different blockchains can kind of do their thing, but the actual means of compressing their computation it's the same mechanism, which means that we get blanket good security guarantees. Unfortunately, Polkadot relay chain and parachains model still suffers from persistent state partitioning. Yeah, we got rid of the patchiness of it all, but you still have this persistent state partitioning. The different parachains, or the different sort of L2s on Polkadot, each have their own kind of state, and it's really hard for them, or it's rather expensive, more expensive, slower, and harder for them to interoperate compared to if two things inside of the same parachain want to do so. Now, this is something that Polkadot is moving towards fixing to an extent this year with the Polkadot Hub, which is essentially building a much faster chain that is where everything can sort of live, and everything then gets sort of amalgamated into this one fast chain that goes 3 times the speed of any other chains and could potentially go up to 12 times the speed of other chains. But it's still not sort of fixing the system as a whole, or at least not fully. This is where I want to talk a little bit about size synchrony antagonism or size coherence antagonism. Now, this is a general principle. You can see it all over the place in various different fields. It's sort of the reason why the dinosaurs got only so big, why single-celled organisms only got so big. As you get bigger, as you scale up a system, you have to reduce coherence somehow. The universe simply can't handle totally coherent big systems. It has a thing called the speed of light, which limits how coherent a big system can be. Yeah? And we already know like physical limits for how coherent a big system can be based on things like the speed of light. But actually real world systems where humans would be interacting with them, their limits are much, much lower because they're not light-based pure information systems. We see it play out in CPU design, right? We see it play, the numbers of places are astounding. It's everywhere. And the reason that it's everywhere is essentially that as a system grows, and its state grows, right? The different bits of state will tend to be farther apart, right? If we look at the distribution of distances between pairwise state components, that distribution will exhibit a greater mean as the system grows and a greater variance. Yeah. So the system, its bits of state will be farther apart from each other on average, and will have a greater variance of distance between each other. Yeah? This means that overall it will run just slower because different parts of the system will take longer to interact with each other. And it means that there will be a greater divergence in how fast small subsystems can interact with each other compared to the state as a whole. Yeah? So if we limit our interactions to just a smaller part, then that part will be able to go increasingly faster as the system grows, as a proportion at least of the system speed as a whole. This leads us to understanding better why we make this persistent state partition. We do it because there's actually no other way of keeping the system going quickly and scaling it out. Yeah? It's just a physical necessity. But if we were allowed a free reign over this, if we could disregard physics, yeah, and just say, right, what do we actually want? All we actually want is a system, that's the big border, thick border around these arrows, with lots and lots of sort of actors, right, each doing their own thing and interoperating as they need. Yeah, freely. That's what we would like. That's what we're aiming for. That's the ideal situation. I only drew, 9 or 10 arrows here. Obviously, we want lots of arrows, right? Ideally, infinite arrows. So we can have lots and lots of discrete actors, discrete, pieces of functionality, all just doing their thing. All right, so if we take this visual language and try to fit some of the systems we've already engineered to it, what do we get? Well, Ethereum 1 was the original decentralized computer. If we think of Bitcoin as a calculator, at least. And basically what we're doing is we have a few different bits of state, right? Smart contracts. And these things are taking it in turns to execute, right? You can run one smart contract at a time, right? As a system, Ethereum as a whole processes everything synchronously. It does one smart contract, then another smart contract, another smart contract. This is Ethereum 1. And then it actually stops for ages while a block is being distributed and re-executed, and we're replicating the state across the world and assuming that some of the computers of the world might be quite slow. And then we start again. Yeah. If one of my calculations, back of the envelope, if the work of a block, all the smart contracts that Ethereum, all the transactions that Ethereum is processing in a block, is really bad, is the most pessimistic work it can do. It's the most intensive work that could be done with that gas limit. Then it will use about 1/16 of the time of a regular computer to process the rest of it will just be idle. Yeah. It's got quite conservative limits. Now, rather than, if it's only processing one thing at a time, then we can actually create a slightly easier formalism, which is just, or easier visual language, which is just, well, we'll just have one arrow for that. We'll just assume it's one arrow that's executing all of the time instead of a few different arrows. And essentially, this is a way of just building a bigger state from these smaller state pieces. Yeah. So we just basically say, well, actually, the state is all of these smart contract state amalgamated together, and then we just have one arrow that sort of runs through them. Yeah. But it's still just one arrow, still one execution thread, conceptually. So we've got high-performance synchronous chains that really try and take this model to the max. Sometimes they can actually even parallelize on the same CPU, so they can do a couple of things at the same time if they know they're not going to collide with each other in terms of their usage of state. Of course, it's on the same CPU, so they're limited in terms of CPU threads. Maybe they can do it 4, 8, 16 at a time, but if we're talking large scale, it's still essentially just a thicker arrow. And we might be able to get them to reduce this idle time between blocks. Yeah, and there's a few tricks that you can do to make that happen that some of the high-performance synchronous chains out there are doing. It generally makes the systems more fragile, but you know, if that's your trade-off, that's your trade-off. Not very Web3, but there we are. Good. Okay, so we move to like independent bridged chains, and we get this. We get like multiple of these systems, but we have to go outside of the overall consensus to interact, right? And that's the insecure bit. That's why it's only in a little dotted gray line. It's out. The bridges are sort of outside of consensus, and the bridges will only go at essentially the weakest link between the bridge. We also have to have lots of different bridges. Yeah. And then we end up having to do hops and routing tables and all the rest of it. So what did Polkadot do? Well, basically it said, let's have a single state system, right? But like with lots of different execution threads, these are the different parachains, and just partition it up, have a fixed partition. So the different parachains sort of exist in their own space, but under the same security umbrella. And that means our bridges, unlike with Cosmos, are on the inside, not the outside, and all of the parachains can actually enjoy the same level of security. We end up with shared security, which gives us an overall much higher level of security. Now, notably, we're still dealing with the arrows are still disjoint, right? So there's not a single arrow, but different arrows. They're different at like one arrow and then another arrow. Yeah. These different arrows pertain to the fact that it can only do processing within a block. And at the end of the block, it has to pack up and leave, right? And then it will start processing totally separately in the next block. Processing has to finish and then kind of start again. And this creates very weird disjoint software. It's like your software cannot assume that it will be able to run longer than a single transaction could run, which means longer than a block will run. You've got a fundamental limit of computation, a fundamental limit on how complex the software which can be deployed into these systems can be. Now, this limit goes up when you allow software to run for the whole block, like in Polkadot, as opposed to relatively smaller transactions with the original Ethereum's very low block size. But still, it's limiting. Okay? You can't do things like infinite loops, right? Or migrations that might want to take all of state and do something to it. Yeah, this is hard. Well, this is Jam. So Jam is what we might call a reactor chain with that provides composition and coherence with sideband shared memory coprocessors. Yeah. So let's take a slightly deeper look in this. So firstly, on the left side, we have this data lake, right? You can think of this as a shared storage system. Memory, shared memory. Memory can be read from it, and memory gets written back into it. Data is read, data gets written back into it. Notably, it's unified. It's a single storage resource for the whole of the system. This is already different to some of the other systems, to basically all of the other systems that are attempting to distribute work. In the middle there, we have our coprocessors. Jam actually has 341 of them, but I didn't want to complicate it with 341 sets of arrows, so there are 4. But there's lots and lots of these things. And these things are basically just high-performance processors. I'll go into the performance in a second. They're still in arrows, right? We still haven't fixed this Turing complete problem thing of having to stop computation and then restart, right, in a bit. Yeah, we still haven't fixed that. But we are starting to build the pieces for fixing that. Now, after computation is done in this coprocessor unit, the outputs of each of these chunks of computation are sent on for synchronization, right, for coherency. So they're sent on into an actually coherent system, what we would normally call like an L1 blockchain, where they can be scheduled in sequence in order to essentially change the overall state of the system in some finalizing way. Okay. Good. So, Jam introduces a concept which is called the core model. This is actually not particularly new. Polkadot also has cores, but the thing is, Polkadot comes with this baggage of managing parachains. It doesn't allow for the possibility of this on this right side of the diagram of the output of parachains to be composed or made coherent in some way other than as if the output is coming from separate chains. So Jam is a generally coherent system with transient decoherence. What do I mean by that? Well, the system as a whole cannot be considered coherent because at times the system is in, these things, these arrows here, don't directly relate to each other. They are independent pieces of computation. They have independent memory that they can draw upon. So in between these, while these arrows are happening, the system can't really be said to be coherent. But after these arrows happen, and specifically when we get to sort of this point here, so in between these arrows, the system can be said to be coherent. Essentially, it becomes coherent every frequency that these arrows are broken, which in turns out is 6 seconds. So every 6 seconds, the system sort of reaches a coherent state. And crucially, because it has a storage facility that is shared, it allows this coherence, this overall state, this overall data silo, to be part of that coherent system. Again, it's transient. That data silo may have changes coming in from the last arrow. So it's only every 6 seconds, once those changes are in, that it reaches coherence again. But it does at least reach coherence regularly. This is unlike persistently partitioned state systems that are just persistently decoherent, right? The different partitions retain their own state, and the system never really reaches a point of coherence. That state is always there and never over here. If you want any effect from that state to happen over in this state, you have to kind of go through this messaging system, which is slow and just generally a different thing to regular computation. How do we manage it? Well, we have essentially 2 different models of execution. We have what are called in-core execution, which has access to this big data lake, but is otherwise stateless. And then separately we have on-chain execution, which is stateful but synchronous. And the data lake, for what it's worth, is quite large. It's about 1.5 petabytes, and has an inter-core synchronization latency, which basically means if one of these arrows writes out into the lake, the information, that data, will be available to another arrow 6 seconds later. But that's intercore, and within a single core, so there is some degree of affinity to cores, which is this grey line here between the arrows. If it's in the same core, that 6 seconds goes to 0, and you can always read out stuff that you wrote last time. Yeah, this is a bit similar to how CPU parallelization works, right? So CPU cores share the same overall memory. When one CPU core writes to memory, that write will take effect immediately from the point of view of that CPU core. It will be able to immediately read that memory back again. It will say the right thing. But if you're on another CPU core, when you even if it happens physically later, when you read that piece of memory, depending on precisely what your coherence model is, you might get old data or it might stall. In our case, we definitely don't want old data, so we always stall. But it's always going to do the same thing, regardless of which core we're on, right? Which CPU core we're on. It will always do the same thing. It will just might take a bit longer to happen if we're in a different part of the system. For what it's worth, the sort of datum size of this distributed availability system, this data lake, is 4 kilobytes. 4 kilobytes, why is it 4 kilobytes? Well, it turns out 4 kilobytes is very helpful for what we're going to do on Jam. If you're more familiar with Ethereum terminology, you can also describe Jam in this way. It's got secure, quote-unquote, Turing-complete stateless rollups. The quote is that, computation is broken into segments. It's got one Turing-complete, quote-unquote, that should be quotes there, smart contract chain. That's the consolidating chain on the right side. How do we achieve this? What technologies are we using? Well, we use the same means of compression of correctness, or roll-ups, as Polkadot. This protocol that we use is ELVs, it's called. I like to call them cynical roll-ups. But I also like to call optimistic roll-ups pessimistic roll-ups, because they take a very pessimistic view of the world. Wait 4 days for the possibility of some fraud being reported. We also have a zero-knowledge proof-based block authoring system that provides block authors with anonymity before they actually produce the block. This substantially reduces the chance of them being DOSed and the network being stalled in that way. Some attacks on the network do require stalling of block production to execute, and systems that do not protect against this risk getting those attacks eventually. We have a near instant finality system, Grandpa, which is adaptive to network traffic. If the network traffic is high, Grandpa will just finalize slower, but it won't stop finalizing at all. It's just it will finalize maybe with a block or two latency. Again, this is already deployed in Polkadot, and it's working very well indeed. Possibly the most important piece of the puzzle is the PVM. The PVM is a new virtual machine specification. It's new instruction set architecture, based in large part on RISC-V. It's very fast and it's very normal. By normal, I mean you can write normal code and expect it to run normally. Unlike, for example, on the EVM, where you kind of have to write in Solidity and it's not going to run normally. It's going to have things like block gas limits and all sorts of stuff. I'll go into that in a second. Right, the Jam pipeline. What happens when you do stuff on Jam? Well, firstly, when you send information to Jam, like you would send transactions to a system, a regular blockchain system, you that information will go through 3 stages. Right, that data that you're sending, that transaction, if you like, I mean, we don't call it transactions, but it's a little bit like a transaction. It doesn't have a signature necessarily, but it's a bit like a transaction. It has data. We'll go through 3 stages of computation. The first stage is the authorization stage. This goes through whatever code we have specified is the authorization code. And it happens in core. It happens in this very, very high performance distributed environment. After authorization completes correctly, if it doesn't, then it just gets thrown away. If it completes correctly, it goes into the refine stage. This also happens in core, in this high performance, high bandwidth environment, but stateless. It's at this point that this is the heavy lifting. This is where most of the work should be being done. Yeah? We move from the authorizer code into the service code. And finally, after refine, the output of refine gets sent into accumulate. This is still the service code, but instead of running in core, distributed, stateless, fast, high performance, it runs on chain. Synchronous, coherent, and it basically integrates the effects that refine says to integrate into the rest of the state of the system. This is the model for how this machine works. So when data comes in, authorize, refine, accumulate. Why do we do authorize first? Well, the machine doesn't have the concept of gas, really, or at least of gas pricing. Instead, computation on the machine is pre-purchased in much bigger chunks. Because it does so much computation, it doesn't really make sense to be charging hundreds or thousandths of pennies for discrete, tiny pieces of work. This would just bog the system down. So instead, it just charges for 6 seconds at a time on a core, plus a bit extra running on chain, right, for making it coherent, integrating the effects. This is a huge amount, right? 6 seconds and 12 megabytes of data bandwidth is what you're getting as a single unit. That's what you're paying for. Now, every one of these 12 megabytes, 6 seconds of computation time parcels has an authorization attached to it. Basically, the authorization is a succinct way of describing what work you want it to do, it to be used for. Because we don't necessarily know that the agent who is creating the work is the same person, organization, identity as the agent who has purchased the ability to do that work. It might, for example, be a parachain, where the parachain itself has purchased it with its own tokens or whatever, and then a collator or a validator of the parachain is creating the block. Well, that's not the parachain, that's a validator or a collator. So what the parachain wants to do is give them the permission to use this time on this computer to move the parachain forward. They can't do it directly because they are the code that would be being moved forward. And this is how we break that problem. So shared state is arranged into services. Services are a bit like smart contracts, right? A bit. There's a bit of a difference. There's a few differences, actually. One of them is just what I've talked about, which is that instead of paying for gas sort of per transaction, you buy time on the computer at a much bigger scale. That's one of the sort of reasons that services are a bit different. Another one is that the computation is staged, which is that it goes through these 3 stages. Well, actually, refine and accumulate, really. But it's pipelined, which means that at one point, refine might be running, and at the same time, accumulate might be running. In essence, 2 different things could be happening at the same time. That's where we get that sort of pipelining from. And it's distributed, which is to say that the same service might have multiple refines running at the same time. Yeah? Those arrows are not necessarily different services. They could be the same service, each running refine, each one eventually giving its output into the services accumulate. Services can scale out over the cores. This is a big deal. And finally, as you might expect, given the distribution and pipelining, services are generally asynchronous. In particular, service interactions are asynchronous. If one service wants to interact directly with another service inside of Accumulate, that interaction will be asynchronous. It will send a message, and that message will eventually be received by the destination service at some later time. This is very different to how Ethereum works, where when one smart contract calls into another smart contract, the execution is instant. It's a call model rather than a post model. Yeah? Jam is a post model. The same is true if one service inspects another service's state inside of Accumulate. It will see the state of the inspected service at the point when the execution started to run, not at the point where it might be now. Yeah? If it's somehow something else has happened in the meantime, maybe it did something. Maybe the destination, the read service is the first arrow to happen, and the inspecting service is the second arrow to happen. If the inspecting service attempts to read into the first arrow's state, it will see what happened at the beginning of this whole chunk of execution. Yeah, we don't enforce any sort of ordering at the point of accumulation. This is to allow for the possibility of parallelization at a later stage. All right. Jam is permissionless. Anyone can deploy a service. So it's a bit like a smart contract platform in that regard. There are the limits for code and data sizes are actually just economic limits. They're just disincentives. They're not artificial limits. We don't place artificial limits on them. It's agnostic to higher level things like staking, economics, and governance. Jam doesn't care. Jam is really just a decentralized computer. It's not trying to create a DAO or anything like that. Right, let's dig into the PVM a little bit. So the PVM, Polkadot Virtual Machine, is an ISA, instruction set architecture. It's based on RISC-V. RISC-V, if you're not familiar, well, it's also an ISA. It's a RISC ISA. It's open source. It was designed by an academic, or a team led by an academic. There are a number of hardware implementations of RISC-V, quite a few actually, so you can actually buy these things as chips. We're not going to use those chips, but it's possible to buy them. RISC-V code can be recompiled very easily into PVM code, right? There are some differences in terms of some of the instructions, but PVM is very clearly a derivative. Inherited from RISC-V is 64-bit registers and a 32-bit address space. So this looks like a real computer, like a physical machine. It's not like EVM at all, which is very much not designed to be a physical machine. The address space is paged in 4 kilobytes. 4 kilobytes, same as the segment size. Yes, indeed. It's Harvard architecture, so we don't have to worry about accidentally overwriting code at any point. Now, very, very importantly, PVM code can be recompiled in linear time, actually very fast, to x64 machine code and to ARM64 machine code, as it happens, right? PVM is actually a really efficient, simple way of, in a consensus-sensitive fashion, expressing regular silicon machine code. It's relatively small. It doesn't take too long to implement PVM. And it's actually quite well suited for dynamic metering, for sort of tracking the gas usage as the thing is executing, tracking the number of steps that have been taken. We've measured about a 10% overhead so far. It lends itself well to continuations due to the stack being stored inside of this 32-bit address space rather than outside of it in some opaque data structure as with WebAssembly. When we execute code on PVM, recompiled native, compared to just compiling it directly native, we observe roughly 45% of the execution speed. This again is crazy fast performance, right? Refine, so let's take a look at some of the numbers. Refine accepts about 12 megabytes of data, which can be either totally extrinsic to the system, totally foreign data, or data fetched from the data lake. It can yield into accumulate up to 48 kilobytes of data. This is per work package, so per 6 seconds on a core. It can execute of those 6 seconds for about 5 seconds of PVM gas. This means taking that 45% number into account, between 2 and 2.5 seconds of regular hardware, physical CPU time. Yeah? Very high performance for blockchain, for a consensus system. It gets information on everything that's being processed during this 6 second interval on its core. So if you want to kind of have two things become causally entangled, right? Two services, independent services, actually sort of interoperate. It makes it a bit easier because you can automatically look to see exactly all the same information that service is seeing. And you can, we have a sort of concept of a ROM or a firmware that is available to all cores at all times. And you can pay to have data placed into this sort of firmware. And then that's basically free to read. Very interestingly, you can invoke new instances of the PVM. You can create and invoke instances of the PVM, filling its memory with whatever data you want. This is a big deal. I'll come back to that in a second. In accumulate can receive one or more outputs from the refine stage, right? So if lots of things are refining at the same time, and then they will all of those outputs flow into a single invocation of accumulate, and it's up to you as accumulate how you deal with the fact that there are many different things to process. Yeah. Accumulate will only execute for about 10 milliseconds of PVM gas. Yeah. Now this is obviously a lot smaller than 5 seconds in refine, which is why I say refine does the heavy lifting. Accumulate does the synchronization. Yeah. Accumulate makes everything coherent again. Accumulate stateful, so you can look at state of the whole of the system, look at other services' state, send messages to other services that are asynchronously interpreted, and alter your own state. Oh, and accumulate is the only place that you can create services. There's no other way of creating a service. You have to be in accumulate and make a call out of from accumulate to create a service. This is unlike smart contract platforms like Ethereum, where transactions themselves can create smart contracts. We don't have that functionality here. It's much purer. Only existing services, the logic of existing services, can create new services. This means that when you start a jam chain, you better make sure there's at least one service on there in the genesis state, which lets you create other services. Otherwise, you're going to be stuck. Yeah? All right. So jam has an authorization model. I touched on this earlier. I'm going to go a little bit deeper into it now. So it has two data structures held inside of jam, held on the chain. These data structures are associated with cores, with those arrows, the lots of arrows, this co-processing system. Each core coprocessor has these two things associated. It has lots of other things associated with it, but these two things are what I'm talking about now. It has a pool and a queue. The pool specifies which authorizers, holds a commitment to every authorizer that is allowed, or every authorizer that is allowed to determine work to happen on this core. Yeah? The ability to place an authorizer into a pool allows you to use a core. It allows you to say what sort of thing that core should be being used for right now. When you buy time on Jam, you buy the privilege of placing an authorizer into the authorization pool. That's what you get. And every time an authorizer is used for a piece of work, it gets taken out of the pool and thrown away. Yeah? So it's sort of like a ticket. And in order to use a core, your work has to sort of prove itself to one of these tickets floating around in the pool that yes, it's allowed. It should be allowed to use the core. And when it does, the ticket gets removed. Now we have a queue, because of course if it gets removed, well, hold on, what replaces it? We have a queue. The queue is actually just a rotating queue, 80 tickets that sort of get copied and placed into the pool, one per block. So every time we remove one from the pool, we put a new one in from our queue. And essentially, when you buy chunks of core time, you actually get to set the queue, not the pool. Yeah. So you basically set the queue, and then the queue will automatically replenish the pool. The reason that we do this is it's all asynchronous. So some work might arrive in some nodes before other work arrives. So we need this sort of level of getting flexibility as to when any particular piece of work should be processed. What do authorizers look like? They're basically a function. And the parameters to the function is parameterizable. There is a way of sort of configuring the function, which we call a param here. That's this thing, param. And then the function takes two arguments: the core index that it's running on, for what it's worth, and some data token. And it can either panic, fault, trap, stop, like, this isn't good, or it can output some data. If it outputs data, it means that the authorization is okay. It gets to choose what data it outputs. The combination of the function f, the hash actually of that PVM code, and the param, those two things hashed together give you the commitment that has to be in the authorizer pool. So you basically say, I want this function to be the thing that that authorizes the work that I want done, and it should be parameterized in this way, and then you hash all of that, and that's what you put in the pool. That's how Jam knows how to recognize the right work to be doing on a core. When authorizers run, they can't just use arbitrary amounts of gas. That would be a potential spam attack, right? So they're quite limited in terms of the amount of computational steps that they can do in order to get to a conclusion of either data or trap, panic. And then any data is fed into the refine stage, and actually into the accumulate stage as well. Okay, this seems like a pretty sophisticated system. It's like, what's the end game here? Because I gave you this like picture with just the arrows going down, and Jam doesn't look like that. So what, that's the ideal thing that we want. How are we going to get there if all we have is this quite sophisticated system? It doesn't look like that. Well, the answer to that is CorePlay. CorePlay is the service that we want to make on Jam beyond a service that is compatible with Polkadot. To understand what CorePlay is solving, we have to sort of rewind a little bit back to the previous stuff that I was saying about partitioning. Why do we have more chains or more L2s? Well, we want to scale out. It's not so much about specialization or sovereignty. It's really about scaling out. What's the problem with using lots of chains to scale out? Fragmentation, right? Persistent state partitioning leading to fragmentation of state space. Why is fragmentation such a big problem? It limits network effects between the different portions of the system. Limits the use cases, limits atomicity, limits developability. If you're a developer, it's actually hard to develop an application over multiple state spaces, like very hard. And as a team who is looking to deploy somewhere in this mad blockchain world, it kind of forces you having to decide where to deploy without really knowing how things are going to be like in the after deployment. Once you're deployed into a particular L2 or a particular ecosystem, it's really hard to move away, yeah, because state is partitioned, right? Those walls are thick, and that's not so good. We don't want this walled garden. Yeah, we want a big playground. So let's go back to the thing. This is what we're after, right? This is what I was sort of saying was what we want. We want just lots of different state machines, all kind of doing their thing, running, Turing complete, and interacting where they need. That's Jam. That doesn't look like that. See, they're different. This is quite complex. But Jam, as I said, is really the sort of the launch pad. This is core play. This is the computational model of core play. Now, we can't do this properly. This is physically impossible. Yeah? Like, physics prevents us from doing this and making it scale to the degree that we would want. So we have to have some sort of management of this coherence, right? We cannot have full coherence. We have to manage the decoherence in some way, but we want to manage it in a way that doesn't impact too deeply on our ability to have atomicity, our ability to develop well, our ability to deploy and not worry too much about maybe wanting to move around somewhere in the future, our ability to have good network effects. How do we do that? Well, I mean, the solution is relatively simple when you look at it. We have agile state partitioning, not persistent state partitioning. We partition the state as it needs to be partitioned, as it's economically sensible to partition at any given time. You can think of core play as essentially a smart contract operating system for Jam. Yeah? It provides a platform on top of Jam for smart contracts to exist. They're actually better than smart contracts. Core play allows for actor-based smart contracts. Wow. Now, one thing you're going to notice here is that unlike these other systems, these arrows are not disjoint. These arrows go all the way from the top down to the bottom. What does that mean? It means that we have actual Turing completeness. Right? It means that we don't have this per block, close everything down, forget everything, go back, new slate, start computation again, that we have with regular smart contract platforms. We have actual Turing completeness. How do we manage this? Well, we essentially provide a platform, an execution environment where the software running on it doesn't know about blocks, doesn't know about transaction sizes or anything like this. Yeah? We provide an execution environment that is really just similar to what you would get with an actor system, an actor model. We still, because everything is operating conceptually in the same state space, allow for the possibility of global atomicity, the possibility of having atomic interactions between any two portions, with any two items within the state space. Essentially, we allow for the possibility of synchronous composition and yet still provide Turing completeness. It's built on Jam, and therefore it's designed to be elastically scalable across Jam's cores. It can use as many cores as is needed. As you add more actors to the system, it uses more cores. It's elastically scalable. It scales out, not up. And it enjoys no persistent state partitioning, so we don't get this fragmentation, either network fragmentation, L2 fragmentation. This isn't a thing in core play. So how do we manage this? This seems like having your cake and eating it. Well, firstly, we use Jam, right? So we have this distributed decentralized data lake. That's where the actor's state is stored. It's available across of Jam, so we can actually don't have to worry too much about storing any particular actor in any particular place, like we would on a system like Ethereum with L2s or Polkadot, yeah? Where we have to store an actor or a smart contract in a particular parachain, particular L2. Don't do that with Jam. They all have access to the same data lake. We just stick it in the data lake. With Jam, we have pipelining. This allows us to speed a lot of things up. We have distribution. We can use all of these different cores at the same time. And with Jam, we have PVM. PVM is crucial. PVM is what allows us to have this apparently continuous execution model, this actually Turing complete execution model. We distribute our state into much smaller pieces than a blockchain system would. Polkadot, for example, distributes its state, its overall state of Polkadot, into quite large pieces. We call these pieces parachains, right? The state of a parachain. It makes them quite hard to bring together. Because to bring together two parachains, you have to have a system that knows everything about both. Yeah? And then it picks and proves the bits of state that it needs and sort of does that computation together. It also means that unless you have a really good way of like ensuring that that there is no collisions between the bits of state that you're using and changing, it means there's no way of having two different sets of well, the same parachain have two transitions at the same time. Yeah, this becomes hard because your state is sort of already bulked together in one coherent system. It's really hard to relax that in two independent transitions. I'll go into why I'm sort of diving into that a little bit later. But by arranging state into smaller pieces, smart contract, actors, it allows for easy composability, like essentially co-scheduling, easy atomicity. We also regularly repartition our state space every 6 seconds, maybe even more frequently than that, but at least every 6 seconds. Yeah, as is needed. It may be if the partition is economically efficient, then we end up not rearranging it at all. But it costs us nothing, or it costs us a minimal amount to repartition. Yeah, I'm not going to go too much. These are sort of other ways of doing things. One of the other ways of sort of trying to get something like this would be to work not at the level of smaller state machines, but at the level of like whole L2s, right? Whole rollups, whole parachains, and just trying to co-sequence them, right? So basically having these giant machines that track both chains, manage 2 transaction pools or more, and then try to causally entangle transactions across them. Now, this has a lot of problems with it. Theoretically, it's like you can do it, but you will end up with, ultimately it will be unscalable, right? You might be able to get somewhere with 2 or 3 chains if you can get a lot of validator support, but there is a huge centralization bias for it. Now, the big scaling issue here is that suppose we have 2 transactions on different chains that are causally entangled. Maybe it's some sort of atomic swap. Now, if we're doing this in a Turing complete fashion, which is of course what we want, then that transaction, those 2 transactions have to be kind of paired, right? Either both happen or neither of them happen. This must necessarily be the case. If only one of them happens, it's a big, big problem. And if one of them happens and then, the other one can happen, but actually something else mutually exclusive happens, which is what we have to assume is a possibility, then we have a big problem. Then we have to kind of rewind the other one back. Yeah? Which means we kind of have to limit finality or limit the effects of any causal transactions until we know for certain all of their counterparts on the various other chains will definitely take effect, now or the future. This is, as I say, this can maybe be managed for a small number of chains. It becomes very difficult when we bring in lots and lots of chains. Basically because we have an order n squared problem, where every chain has to track every other chain's transitioning and be certain that all of the other chains are going to do what they think they will, what they say they're going to do, what the implication or the requirements of this particular effect should be, before we actually go ahead and do the effect ourselves. We kind of all have to either all go into the room or no one go into the room. But we can't possibly have any people that look like they're going into the room but actually stay outside. That's a big problem. So we have to track entanglement. We have to create entangled blocks. Creating entangled blocks across chains is no easy thing either. We have to essentially make sure that our transactions get in at all. Not so easy. And then we also have to track the opportunities for entangling. And then if we want to have many different sort of producers all doing their co-sequencing, then we have to we have a sort of further issue where, in essence, we're trying to make sure that the two different producers don't sort of collide in their co-sequencing attempts. Essentially that if we're co-sequencing 5 chains, then we don't get sort of 4 producing blocks, but actually one ends up being part of some other co-sequenced set. The effective, the end of the road for this is centralized sequences, right? The end of the road for this is just having one giant machine that sequences everything and knows everything. This obviously isn't very Web3. There's also intent solvers, but these don't solve the same problem. They can help. They can help to some extent if we want to use multiple chains, but they don't solve the same problem. Good. That's the talk. Thanks for your attention. You're a very good audience. No talking at all, not like in some of the other places we've been. I am now going to give you a quick demo of Jam. Let me just over to my demo screen. Where are we? Here. Okay. So I want to sort of show you a couple of things here, and I have actually. Oh dear, I don't have a pointer. Oh dear, that's not good. How do I find where I am? Okay. I want to show you a couple of different things. One of them is the demo service. So here is a example service in Jam. I hope you can see that. Is that readable? At the back, yeah, just about. All right. Good. Here is a demo service. As you can see, this is Rust code. We have just a declare service demo, and then we're implementing we have 3 different functions in our demo. On transfer is what happens when it receives a message, and then you already know about refine and accumulate. Refine is what happens in the core, accumulate is what happens on the chain. We get a few different parameters to refine. We get the service ID. This is the instance of the demo service that is having refine being run on it. We get payload, that's the data that's essentially the transaction data, if you like. And then we get information about the sort of context that this thing is running in. We're not going to use that, so I'm not going to go too deeply into it. And we can give some work output, some data out of this. So we kind of, this is like you can think of this as like a main pre-processing stage for accumulate. First thing that we're going to do is we're going to fetch the output that we got from the authorizing agent, the piece of code that ran that authorized us to actually run on Jam at all. We're going to print a message. As you can see there, this is the refine in the demo. This is refine in the demo service. Gives us the ID with payload length, and it gives us the payload length. There's actually a length in there. And then we have we're going to make a message by formatting this like message string and export it into our distributed availability store. And then we're going to encode and output the place in our availability store that is sitting, the payload itself, just straight, and the output from the authorization itself. We're just going to encode that and output it into accumulate. If we look in accumulate, what's it doing? Well, it's printing a debug message, and then it's going through all the refines that it's getting, which is actually probably just going to be one of them. And then it is decoding the refine output, so it's extracting this ID, payload, and auth output, and it's just sticking them in the state of the service. Yeah, this highly coherent state. For the ID, you are formatting it as a string rather than putting it sort of directly as a number. I'm not going to go into on transfer quite yet. I compiled this earlier by running Jam pvm build. I'm not going to do it now. It takes a few seconds, and I want to get on with the demo. Okay, so we have a REPL here. REPL is just like a command line interface for using Jam. What this does internally is it sets up a small Jam testnet sitting behind it, and it doesn't just author blocks all the time like it would do normally. It authors blocks as we tell it to author a block or as we need a block being authored. We have this instant extend, which means just author a block as it's needed. So we have, if we look at the services, which we can find by ls, then we can see there is just one service called the Bootstrap service. This is a general sort of Swiss Army knife of functionality that allows us to do things like create other services, transfer funds, alter what's the authorizing agent, the authorizers in our authorization queue, and lots more. It basically gives us super user access, administrative access to the jam machine. We also have the concept of a default service, which is the service ID that it uses if we don't specify a service. This is sort of like the current directory, so to speak, but in jam terms. Right, so let's start by creating a service. We don't want to assign, we're going to just create service. I already compiled the PVM, the demo service, this code over here. If we have a look in our directory, we'll see demo-service.pvm. So let's create that. To do so, we have to hash the data at demo-service.pvm. It understands that I got the data for the hash from demo-service.pvm, and so we'll feed that into the service automatically as its data. Basically, it does a lot of stuff that we would normally as far as jam is concerned, is like individual steps. It sort of amalgamates them together as much as it can so that I don't have to do too much faffing around. We need to give it a bit of balance so it can store some data in its storage, because we know that that's what the service is going to do. For any data that you store, you have to have some sort of balance in there, like a minimum balance. So if you're familiar with Polkadot, it's like the existential deposit. I don't think we need that much. I'll put 1,000 in. And there we go. So looks like it's worked. It's telling us our default service is now A. This is services actually have these kind of long numbers in here, 32-bit. Sorry, 32-bit. Yeah, 32-bit identifiers. But typing in a 32-bit identifier is a bit of a pain. So the CLI gives us just letters to use. If we list the services available, we see there's now 2 services. And for what it's worth, I can CD back into 0, and then it's the 0. I'll CD back into A, and there we go. Good. So how do we do something with a service? Let's make a work item. A work item is like a sort of transaction for a service. It doesn't necessarily have any sort of signature. It's just general data. What would be the signature is actually the authorizer, right? And you might be running, hold on, what's the authorizer? I'll go into that in a second. For now, you just need to know it's looked after. It's taken care of. So we're going to make a work item. We start by saying work item, and then we'll have a work. We'll just give it hello world. Oh, item hello world. In fact, let's do better than that. Hello Taipei. Okay, good. Now it's like telling us, all right, you've made one work item, it's pending. Now we want to package that up into a work package, one of these 6-second whatever parcels of execution, and give it over to the chain, get it guaranteed and into the system. So we say we use the term guarantee for this. And what it's just going to do is take this work item, parcel it up, and feed it through the system. And there we go. We can see now we get similar debug messages actually to when we created the service in the first place. If you remember, the creation of a service actually needed a work item to be created. We didn't specify it explicitly. We let the CLI do that for us, but that's actually what's happening behind the scenes. And yep, it looks as though it's been guaranteed. We don't know we know that the 2 debug messages have been printed. One that's in the refine, and it says that the payload length is for 13. That looks about the right size. And then we get 1 item into accumulate, so that looks about good. So what are we expecting? Well, if we go back to our code, we're expecting firstly something to be in the distributed availability system. We're expecting this message from the refine logic. And then secondly, we're expecting a bunch of storage items to be written into the state of the service, one of which, this last info ID, will help us find this data that we put in the DA system. But first, let's start with the others. So last payload, this is going to be the, should be the payload itself. To read read the storage, we read storage, and then we just tell it we want to know the last payload item in the set. It's actually going to use the default service, which is A. I could specify A specifically. I'm not going to bother. And then it will say, hello Taipei, as we were expecting, hurrah. So that means that, yes, refine has passed this message into accumulate, and accumulate has correctly written it into storage, as we would expect. Now, we can also read storage, one of the other couple of things. Let's read storage of the last info ID. This is going to tell us where in the DA we have it's placed. It's actually only going to tell us the index in the work package. We know the work package hash because it's written here, and then it's going to tell us the index sort of within that work package. Let's have a look, and it says 0. Unsurprisingly, you only wrote 1, so it's got 0 index. So let's see if we can read that from the DA, read segment. Now, for reading a segment, we have to tell it the work package or the segment root. This is a cryptographic commitment. In our case, we only need to specify the first byte, and it knows what the work packages that have been authored are, so it's going to fill in the rest for us. And then we need this 0, and we want the first item. Have a look at that, and then yes, it's telling us that there's actually one segment in this this whole thing. That's its segment tree root. So that's the cryptographic commitment for this, and this is the message sort of in the segment. It says payload is hello Taipei, as we expect. The authorization output is authorization equals nothing, as we will expect when we see what the authorizer is. And then we're also telling us that we've got 4,054 zeros on the end, because this is a 4K segment and we have to fill it with something. So in this case, it's all zeros. Authorization is the empty string. Why? Well, authorization output is authorization equals the empty string. Where is that coming from? Let's have a look at our authorizer. So this is what an authorizer looks like. It's similar to a service, but it only has one function. Function is authorized. This is the single entry point of an authorizer. It gets given the parameter. If you remember, I said authorization codes can be parameterized. Authorizing agents can be parameterized. And then it's also giving us the work package, which is the bunch, the whole thing, right? All of the work, all the description of the work that needs to be done. And it's telling us the core index as well. So it's going to print an information statement. And if you remember, we did get this information statement, null authorizer, lots of information there. It's going to check to make sure that the authorization data is the same as the parameterization data. What does this mean? Well, it means we've parameterized this code with param. That's fixed at the point that we are specifying what is allowed to run on the core. That's fixed by the agent that purchased time on the jam machine, right? That's the one side of the coin. The authorization, the package authorization, that is not fixed by that agent. That is fixed by whoever built the package. What does this mean? Well, it means you can do things like check for a signature. You might, for example, place the public key as the parameterization. You may even do it as your own public key. And then at some later stage in the authorization, when you're ready to actually build the work package, then you put a signature, you sign the contents of the work package. And then the authorizing code will just check that the signature, well, the public key coming from the signature that we verified the signature as having, is the same public key that the code was originally parameterized with. Yeah? That would be one way that you use this, but there are lots of other ways. You could, for example, have a ZK commitment, and you could say, right, there must be a zero knowledge proof in the authorization data that proves that it was, I don't know, one of these validators, or that some particular piece of computation was done correctly inside of the work package. And it's actually that we're checking in the authorizer code. There are all sorts of things that you could do. But basically, you get free reign over passing data in as the purchaser of the gas and proving yourself as the author or the builder of the work package. Yeah. In this case, we're just checking that the builder of the work package has put the right token in, and we're just matching the token up to whatever the person who purchased the gas for the work package has placed. And then we are making a message, authorization equals something, and then it equals the package authorization, right? We're just passing that out. So that's actually where we get the authorization equals empty string from. Why is it the empty string? Well, it just turns out that the default authorization doesn't have a parameter. It's just empty. Yeah. But what we can do is we can have a play around with this and make a new authorization with like a special password. So in this case, we're going to push this CLI thing. We're going to push an authorization into our list of known authorizations. CLI is the thing that's actually building these work packages. It needs to know what authorization to put in the work package. We're going to push a new one in so it can choose this if it thinks it's necessary. We're going to start with just saying, well, we want to use the null authorization code still. That's this code here. But we're going to pass in some sort of token, like a parameterization. We'll make our parameter, just make it type A. And then we can specify what we're going to use as our default work package authorization token. Now, if we say anything other than type A here, this is a useless authorization because it will go into the authorizer and then fail because it's going to check that they're the same, right? So let's make it work at least to begin with. We'll put type A in there as well. Okay, so now we can list the number of which authorizations we have by doing that, and we see that there are now two authorizations. There's our original default one, which just has is null authorizer with the empty strings, and then we have a new one, B, which is the one with type A. Now we will. Now what we need to do. This is all very well. It's not going to use this second authorization because the cause, if we look at the authorizations of the cause, which we can do very easily by inspecting the pool of core 0, our authorization pool for core 0 is this 0x73 hash, which you'll see is the same as A, authorizer A, right? That's why this all works, why it can actually have any work package in at all, because the authorization pool and matches the authorizer that we're using. Now, if instead what we do is we assign to the pool, boot assign, to core 0, another authorization, B, and it says assigned, and actually it needs 80 of these things, so it's going to just replicate the thing 80 times. So if we now look at our pool, inspect our pool for 0, oh, it hasn't changed. No, it hasn't. But if we inspect the queue for 0, now that has changed. That's now 0x29. If we extend the block, the chain, and have another look at our pool, we see that we're starting to fill up with a new authorization. And the more that we extend, in fact, let's just extend it 5 times. Now we only have the new authorization, 0x29. This means that the pool is unusable, or it can only be used with that new authorization. If we delete that authorization, it won't be used at all. Now what we're going to do, go back to our list of authorizations and remove the first one. RA, I'll do it properly. Remove auth A. And we only have now one, and it's this new one, 0x29. That's fine, because our pool is now full of these things, so we have lots of tickets for our authorization to use. Good, so let's do the same thing. Let's make a work item. Work item, let's say, hello again. And guarantee that. We actually have some shortcuts. G is shortcut for guarantee, but I will guarantee it. Now, hopefully, this will do something. And there we go, it is. So it's come into the null authorizer as we want. And it's showing us that the parameter has been now parameterized with the password Taipei. And, but it's okay. Our token, our authorization token is also Taipei. They're equal. So it's going to go through okay. And then we have, we go into the refine and we have a new payload and da-da-da-da. So let's have a quick look, make sure that it has actually changed our storage. Last payload, and indeed it has. That's nice. And it should also have changed. Now if we look at the last auth ID, I think it's auth ID, no, last auth, what was it? Auth param? Auth param? No, last auth something. Last info, wasn't it? If we look at the last info ID, yep, then it's 0. So that means then if we look at the segment root of this work package, so we read segment 0xff and 0, then indeed we now have our new authorization output, authn Taipei, different to the empty string that we had before. Finally, I think we can read the storage of last auth output, and we should get the same thing. Yes. Good. And for what it's worth, if we change our authorization, let's go up and redo push auth, we're going to make this the wrong city. Maybe we get confused and we say Taiwan. And then it's default auth is now OX29. Yes, okay. So let's clear the authorizations, auths, and then add this new auth, and then remove, and then remove the default auth, remove auth, default auth. Okay, now we have a broken authorization, right? Because our parameter, Taipei, is different to our authorization token, Taiwan. This is a bit like if someone tries to use the wrong signature in our example of how to use this in production. Now, if we try to create a work item, hello. It's pending, okay, fine. I try to guarantee it. Is authorized failed, right? It didn't even get through is authorized because the authorization is broken. So let's let's do the same thing, but we'll add just a null authorization. Okay, and then we'll remove our other one. Actually, no. Let's do a. Is this right? Is this going to do anything? XX? No, it won't. Okay. So good. I think that demonstrates everything that I was going to demonstrate. So yeah, there you go. That's Jam doing its thing.
Perfect. Thank you so much, Gavin. Let's give him a big round of applause.